Today we'll learn about the urine anion gap and how to derive it and how to interpret the results. If you've done the serum anion gap tutorial, then much of what we're going to do in this tutorial will be very familiar to you. But if you're starting out with the urine anion gap tutorial first, that's fine, that's no problem. Much of what we do here will be applicable in the serum anion gap tutorial. So again, the urine anion gap or any anion gap formula works on the law of conservation of charge. Alright, and so in a simple mathematical formula, what that means is that the sum of the cations equals the sum of the anions. In this case, we're talking about cations and anions in the urine. So let's go over the more common cations in the urine. Some of those, of course, are measured. Common ones include sodium. We measure that as a urine sodium concentration. Potassium, we measure that. And of course, we have unmeasured cations. So let's change color here and talk about the unmeasured cations. Those could be lithium, if we have any in the system, calcium, magnesium, and one in particular that's very important in the urine and not so much in the serum is ammonia. This is a key reason why we even use an anion gap, because we're trying to calculate the concentration of ammonium, which in some laboratories can be measured and in some hospitals can come back rather quickly, but in most hospitals, like my hospital, maybe even yours, this is not a test that's going to come back the same day you order it. You can use a urine anion gap to estimate the concentration of this, and that'll help you determine how the kidney is handling acid in the body. That's actually how the urine anion gap came into existence, or what the reason was for it being devised. So those are the unmeasured cations. We're going to lump them together and just call them UC. And then of course we've got a bunch of anions that we need to discuss. Excuse me. And those anions are commonly the chloride, since that's the most abundant anion in the body. We do have bicarbonate, sulfates, and phosphates. These are all known as titratable acids, and I'm actually going to write them in yellow because the concentration of these fluctuate. That's why they're called titratable. You really can't predict how much of these you will get or not get in the urine, and so these are just lumped together as unmeasured anions. Of course, you've got other unmeasured anions like lactate. There's some beta-hydroxybutyrate and acetoacetate that may be formed, but these are all in low quantities. Their values can actually fluctuate, so we just lump them together as unmeasured anions. And so we're going to do the same thing that we did in the serum anion gap tutorial. What we're going to do is we're going to put these variables together and then try to interpret what we get. So we're going to call the urine anion gap as UAG, and that's the sum of the cations minus the sum of the anions. Alright, so in other words, we'll just pick our cations, and that's sodium. And this is all in the urine, plus potassium. Now, you may remember that in the serum anion gap tutorial, potassium was excluded from the formula because there's so little serum potassium that it really doesn't make a difference to the total sum of the cations. But in the case of the urine, there could be quite high quantities of potassium. The potassium here will contribute to the sum of the cations, and so we include that in the formula. I'm going to put a star here because there's a particular unmeasured cation that we have an interest in learning about. That's ammonium. And we choose our unmeasured anions. The most common is chloride, and then we lump all the other ones together into unmeasured anions. So let's just rearrange this formula. Alright, so this is of course urine, so I'll just put a U here to make it a little bit more accurate. And this is the formula that we're accustomed to using. And that's our urine anion gap. So let's interpret this. Say we have a urine anion gap that is greater than 0. Well, there's two ways that we can have an anion gap that's greater than 0, otherwise known as being positive. We either have no unmeasured cations, this quantity becomes 0, or we have too many unmeasured anions. Now, unmeasured anions, if we have too many unmeasured anions, like a lot of bicarbonate or a lot of lactate or a lot of sulfates and phosphates, we could have a urine anion gap of 0. Greater than 0, excuse me. But more commonly, instead of having an unmeasured cation of 0, what we have is a low number of unmeasured cations. And the cation that we're most concerned about is ammonia. So patients who have a urine anion gap greater than 0 must have a low amount of ammonium generation. They must not be making enough ammonium. Now, ammonium is the type of acid that can be formed by the kidney when it has a high acid load to excrete. So the quantity of ammonia will vary based on the acid-base balance of the patient. You can only use the unmeasured anion gap when you've got a patient who has a metabolic acidosis. In other words, you've got a patient who has a lot of acid in their serum. That acid needs to be disposed of. The kidney is the primary organ that disposes of acid. It does that primarily by generating a lot more ammonium. But in disease states, the kidney cannot generate a lot of ammonium, and you know this because the urine anion gap, is greater than 0, is positive. So this is your classic renal tubular acidosis. The inability of the kidney to excrete acid because the kidney cannot make ammonium. Now there's a number of reasons for that. Some of them are at the molecular level. They may not have any bearing in clinical practice or on an exam, but you should know at least that when you have a kidney that's unable to acidify the urine in the sense that it cannot make ammonium, you will have an urine anion gap that's positive, and most likely you have a renal tubular acidosis. So in the case of a urine anion gap that's less than 0, well, in this case you must have either no unmeasured anions, and that's hard to do because you will have some unmeasured anions in the urine, phosphates, sulfates, etc., or you have a lot of ammonium being generated. And that's commonly the case here, a lot of ammonia generation. Now the kidney does not generate ammonia just for the fun of it. It generates ammonia when there's a lot of acid that it needs to excrete. This is what a normal kidney does when there's a high acid load. So say you eat a meal high in acids like animal protein, for example. Your kidney will acidify the urine in part by increasing the amount of ammonium it generates. So after a meaty meal, steak, whatever, you can check your urine anion gap and it should be negative. So this is what happens in the normal condition. Right, your kidney is trying to eliminate the acid in the serum by generating more ammonium. This is an unmeasured cation that makes the entire quantity negative. And you can also see this in patients who have GI losses. So individuals who are acidotic because they have, for example, diarrhea, need one of two things to happen. They need their diarrhea to stop in order to return to acid-base balance, or they need to eliminate that extra acid, and they do that by increasing the amount of ammonia they make. And so this is a quick way of understanding the urine anion gap, how to calculate it, and what these different values mean. Hopefully you get a better idea of the urine anion gap. It's very similar to the serum anion gap, so if you understand one of these tutorials, you'll most likely understand the other one as well. Thank you very much.